Yes. Thank you. So I just rewrite the statement. In fact, take a non-scalar term inertia type, take T big enough, then there is the G2 torsor of the Moufang stack, such and cover that, such that we have a model, an explicit model on each chart. So I would say some word of state of the art. So in fact, when tau is generic, so this result was already known. It means that we have a nice description of the Emerton G stack here. So this is due to Karagiani Emerton G Salit and to the same author as before, Young, Levin, and Mora. And why this result is known is because, in fact, this stack agree with so I think that's this one, agree with the module stack of Brake-Hissing module. Brake-Hissing module. Right, so we say I didn't define this object, but I will give you a description of this one. I will not define what is a Brake-Hissing module. I changed my mind, but I will give you a presentation of this object. Okay, so in the case of generic type, we have this nice description, and we know a local model of this object. So since they are the same, that's fine. But the point when tau is non-generic, this is not longer true. Okay. In fact, the tau is only the schema theoretic image of a map from the moduli stack of Brake-Hissing module to the phi module étal, okay, which is another object which I will not define, but I will replace by some things that hopefully I will define. Okay, and in fact, so this is not. You have to compute this this image, so it means that the tau, the Moufang stack, is obtained from the module stack of Brake-Hissing module by contracting the fiber of this map. This map. And the fiber of this map are called the key similarity. Okay. So you have an object and you have to contract it. And this is the source of all complication in the non-generic computation. It's this contraction procedure. And the point is to find a good model for this contraction procedure. In the generic case, the key similarity are all trivial, they are reduced to 1 point, so you have nothing to contract. But in general, key similarity is it's not important. Okay. So I didn't understand the question.
Some kind of resolution similarity?
Yes.
So
Okay. So I would like to give some application of this result. So with my second part. And then some explanation of the result. So I will give two kinds of applications. So first, I will give some property that we can deduce of the Mertenji stack, and then I will give you some property on the deformation ring. So in fact, we have two corollary from this theorem. The first one is that the normalization of this Mertenji stack, the cursor of Z, as a rational singularity, and is Gorenstein. So this rational singularity should be understood in terms of the paper of Kovac. To have a precise definition of this notion, but it means that since we have in fact explicit equation, you can look at this equation and see that the whole object have some nice global property. Another corollary is that in fact the talk is in general normal, but except if the inertial weights, so the coefficient which appear in the talk, belongs to the very bad value 0 and 1. We have only 0 and 1. Okay, and in this case, we can describe the non-normal locus in terms of the rho bar. So the rho bar should be Fontaine-Lafaille. With the weights which are predicted by the weight of time, okay, which is precise weight. Yeah, so we know exactly what is the normal locus. So, for example, K is QP. So this Mertenji stack is normal, except if the inertial type is 1 plus the reduction of the cyclotomic character to below P, and the rho bar is ramified. Fontaine-Lafaille is the corresponding. I would like to say a word on the deformation ring. So I'd like to say that the conjecture are true. So first, so I need irreducible error representation. So type and before. So this is the old notation. Okay. And we assume that this type is compatible with rho bar in the sense that the determinant of rho bar is not same as this character. So if we don't have this equality, in fact, the deformation ring is 0. So for such data, as I told you, is Caruso. We define this combinatorial object, which is a set of 2F symbol between 0, no, it's O, so it's not 0, O, A, B, A, and B. So it looks like a G, or it's a mixture of. So what it means that the case O is a universal case. In fact, when you take a generic situation, you have some O everywhere. Okay. And you can see that you have two characters, the character A and the character B, which is dominant in the situation. And so this is the first character and the second character, and sometimes you switch from a dominant character to the other one. Like you choose this location. And so this we have a very explicit and simple recipe for this object. You write H minus PH plus 1 H minus gamma prime. You write the PID digit of this number. This is minus 1 here. P to the. Okay. And so it's dependent on gamma prime of H, but you can have a similar formula with gamma, but since the two are related.
Sorry, what was that on bar?
The cyclotomic character. Okay, and the rule is if your vi is bigger than 2, you put a O. If vi is 1 and the previous one was O, then xy is O. If it was not a O, you take xy is a B, and for vi equals 0, if it was the previous one was a O, you take an AB, and the previous one was not 0, you take the A. Okay, that's how things happen. So as I told you, this is a generic case. You can believe that. And in fact, this number, because that one character is dominant, the other one is dominant, but sometimes they have to change the role because, as you know, when you go minus 1 plus 1 becomes 0, so something happens. Okay. So, for example, so this is very explicit. You can have a very degenerate gene, which gives you a very bad situation. But life is arising everywhere and give you a very nice animal. Yes.
For instance, actually, the symbol xi are constructed depending the graph I and then it goes down.
Yes, in fact, it's a 2F periodic, and there is so in fact, you have something to prove that it is well defined.
That's already the answer to the question.
There
is no first thing.
Yes, you just have to prove that it works.
So the A, E, and AB are the derivators.
But it's just symbol, and in fact, it's to understand what happens, in fact, in this situation. Because in fact, what we were doing like that. In fact, we are computing some Barsotti-Tate module. So we are writing some explicit matrices, and we have to control what kind of matrices can appear. And this is a way to code what happens. Okay, so for H, so I give you some very bad situation. Really not generic because everybody is 0 or 1 or. And I take this this type. So I like this example because there is a lot of difficulty. So this is for F equals 6. So it means that P has to be this one or maybe. Okay. And for this one, if you compute, it's completely stupid. You obtain this G. But in fact, it was very efficient because you can test a lot of you put on the computer and see what happens. And you realize that almost nothing happens. Okay. And so our first result with Xavier and Agnès was that if you have the gene, so if you have this data, this gives you the kissing variety. So the kissing variety, we prove that it was a subvariety of P1 to the F with explicit expression, which are encoded by this object. And so let me show you how we manage to obtain the kissing variety. As a corollary, we prove that the kissing variety was connected. But once again, it was a way to make some experiment. Right, gene. Zero, F minus 1, F to F minus 1. Okay. So I have to see which is the dominant character. So here, this is the B. Here, this is the A. And there is more A than B. Here, this is the H. So here I don't. Yeah, so this is A. So here it is the A, but here I don't know because there is as much as the A and B. So I say that this one decides which is the dominant character. When I don't know, I take the previous one. Okay. And then when they are the same dominant character, I draw a line like that. And no line here because it's the same character. Okay, so it's a little magic. And now I replace all my letter by element of P1. So I have 6 elements of P1. And when I have a O, it means that the variable is 0. So as you see, if there is a O everywhere, there is only one point in the Kiss variety, and it's very easy. Okay, and now when I have a line, it means that the product of the two elements is 0. Okay. So here I have an element of P1. So since this one is 0, I can choose this one is 1. I have to draw the line. Okay. Okay, that's so. Since this one is 0, I can assume that this one is 1. But since the product of these two is 0, this one is 0. And now, since this one is 0, I can assume that this one is anything. But if it is anything, this one should be 0. So this one has to be 1. And if this one is 0, this one could be anything. But if I take 0 here, so it means that this one can be free. But this one is free, this one is 0. So what it means is that here you have a plan. Okay. There's two products of P1. Here you have a line. And here, this is the point. So this is the case invariant. Okay. So it's very efficient.
Can you explain again how this last line from A to AB, like before it just goes from top to bottom and then
no,
starts?
Yeah, no, it's because I start from the dominant character.
Ah, okay. And that is how you draw the line.
Yeah. Okay. Okay, so it's very efficient way to encode the case invariant. And so what we were very surprised that it was not a surprise that it was an efficient way to encode the case invariant because we construct the subject in order to be able to compute the case invariant. So it's really an ad hoc object. What was really surprised is that the number of command weight, which is also the number of irreducible components of the reducibility of the deformation rate, which is the conjecture with the broad, is encoded also by this object. So there is more than the case invariant inside this object, where it was clear. So that's why we make this all this conjecture. So we conjecture that the ring is determined by the gene, and also we conjecture that there is a natural decomposition of the gene such that the deformation ring should be the product of each species. So let me, this is another conjecture. Let me show you the pieces. So as I told you, the O will play an important role because this is a generic place. At this place, nothing can happen. Actually, so you get two pieces. This is the first pieces, and this is the second pieces. Okay, because it's cyclic. So you have the first pieces and the second pieces, and we conjecture that the deformation ring should be the product of each pieces, which are cut by the generic place. to this one, but this one is a A. So they don't have the same dominant character, or they are not connected. Okay, that's good. Yeah, it's okay with my work. No, but really, this is a way to write how the reminder can go from one place to another. And the main point is that you are generic, nothing can happen. And so in this case, the deformation ring, so it's the product of two pieces. Okay. We write it. One relation. Sorry. And yeah. If you reduce modulo P, you obtain a four irreducible component. Okay, and this is also the four number of tag. So what as a corollary of our result with Bao and Stefano, so all these conjectures are true, as I told you, even in a more general setting, so even for Bao is reducible. There is no gene for reducible, but there is a way to construct it. It does not depend on P and so. Okay. So I would like to say a few words on the proof. At least one idea of the proof. So for that, I need to give you a description of the stack of practicing module. Okay. So, as I told you, in fact, so there's Moufang stack is a schema theoretical image of the break-kissing module, stack of break-kissing module into the stack of field module. So I will say what is this object. So I will not say it in terms of break-kissing module, but I will say it in terms of what is useful for me. So it's a stack of something like this. This is a model due to the long Levin-Mora. So what is this object? So if R is a Noetherian algebra, I have to tell you so first that is this one, and then what is this one, and then what is this symbol. Okay. So first this one for that I need to remember you that this one was this one. Okay. And you have an evaluation map from this one to J2, you send V to 0. Okay. And with this evaluation map, I can define this one as the Iwaori group, which means that this is the inverse image of the board. Okay, so this is the quotient by something which is like a board. What is this one? Okay, write smaller in order to avoid the so this one should be written like that. So I'm sorry for that. We define what the object. So this one, so you remember that two depend of two parameters. This is a family of element of S2, and this is a family of two couple of integers. So this is this family. And V to the power mu g. So V to the power mu g means that you take V to kg and 1. So this is a vector. Okay. And just we change the two coordinates of this vector. Si is the two permutation. And this is a subset of the loop group. So you take the J2 with the coefficient in this ring, and you can inverse the variable V times V over P. And what is this thing? So this is a subfunctor of this one, such where the element satisfies the following property, which are very explicit. The determinant of A should belongs to this ring. So here it's because we are in the Barsotti-Tate case. This is the power 1. You have a 1 here. And you have also this matrices is in fact in value of in this ring. And it is upper triangular. So it's a nice way to write the Voigt-Kissing module. We can make all this happen. And V to speed and -1 have the same property. Okay, so this is really explicit. So you see that this Voigt-Kissing module stack has a very nice description in terms of matrices. It's because this one was a kj and 0. Okay. So I describe what was these two groups, and so there is this phi here. So this is the quotient by the phi conjugation. So it means that the two family of matrices are equivalent if there exists a family of matrices inside this one, such that A plus X G A G X G minus 1. Okay. And what is very important here is that we can cut this object into pieces, at least the F point, modulo P point of this object, we can cut to 3 pieces. So what I would like to say is you have a very nice cover of this object. Like that. You have a very nice cover of the abstract object. And this is, since everything is explicit, you have a way to write a pair of triangular matrices. There is not that many forms, and this gives you the local chart. They come from the decomposition of this object. Okay. Okay. But okay. So what is difficult here? So now you have this object, and you would like to have a nice description of this object, but in fact, there is 2 difficulties. Here you have the inverse matrices, which is not convenient to compute, and here you have the phi quantification, which is really difficult to compute. So you would like to avoid these 2 points. So roughly, the map from the Barsotti-Tate module to the phi module is here you have a nice basis where the Barsotti-Tate module are described by such matrices, and you send these matrices here, which give you the matrices of the phi module, functional path. Okay. So in fact, you will see that this map factorized through something which is less abstract than this one. So I will do that like this. This one. So as I told you, you take a Barsotti-Tate module, which is described by such matrices, and you send it to nice matrices. So I have to tell you where I am here. Sorry for that. What is this object? So this object is really nicer because it's a set of matrices like this, and such that, in fact, I will not send exactly AG on XG. I will send XG on something which depends of V on S, G, and mu. I will and so these matrices have nice property that so the determinant so is inside like that. But the determinant condition is not that difficult. But and also G is the matrices So in fact, AG is obtained by AG, and you multiply by a matrices depending of your mu. So you have an explicit way to pass from, and that's why you see that the KG appear here. So it's I don't remember exactly, but it's something like AG times V. No, because it's not a tool. I will. I cannot say it now, but this is complicated. But the point is, here you have a condition that you have to inverse the matrices, but here you don't have this condition, which is really already better. And as I told you, the main difficulty after it's this fire conjugation. So you have to do something in order to avoid or to control, in order to control this fire conjugation. You cannot avoid it. And in fact, I think it's one of the main ideas is to do something in order to avoid the phi conjugation. In fact, okay, this question here, you can rewrite as a product like that. What is so L1? I remember earlier that this was the kernel of the evaluation, and okay, and so LG was the inverse image of the Borel. So we can prove that you have such a decomposition. So you have your module of the stack of Breuer-Christie module. You look at his image inside this big object here, which replaces the phi eta module. So let me skip some of the decoration. Okay. As I told you, the object we are interested with is the theoretical image of this map. Okay. And then, since we have also this nice decomposition, so L dash is also L1 G plus times G2. So this one, okay, since L plus is this product, you have a nice G2 torsor. So instead of taking the quotient by this product, take the G2 torsor, and it will give you L1G. Okay, so you have a G2 torsor. You take the quotient by this group. So you I don't see it. And then you can take this object. No, the object like that, and then you can take the schematic image of this one, and this is a GL2 torsor over this one. And what I say is that we will describe this object. And the point is that here you still have the phi conjugation, But what is nice is that we can construct a model of this one without the P conjugation, almost this object. Okay, and the point is that, as I told you, I can cut into pieces everybody. So, and the point is that we have. The point is that we have a local model of this object. And the main reason is because here we cannot do the computation at the level of the Iwawi. The computation are too complicated. With this hypothesis on the matrices cannot deal with that. But here, at this level, at the level of the first congruence group, you can manage to deal with the computation. Okay, so let me say a few words on the definition of this model. So I have to construct something which looks like this one, but without any phi conjugation. That's the main point. So what is the model? So I take for this one, so the question of G, as before, by the product of G plus G, and here I take the B-ship conjugation. So it means that xi, ai, xi plus 1 minus 1. So without the phi. So the x here was the same as AG so P conjugation, the product of L with G and B. Okay, so this looks the same, but the main point is we don't have any phi. Okay. So this is our model. So you construct the same object, the equivalent object without any phi here. And then plus G times G. So you have still your GL2 torsor. So you have a subject. And you take this subject like that, okay? And you take the schematic image. And so the main result is that this object that I define without a phi locally is the same as the object with a phi. So the main idea of all work is to find a way to avoid to compute the phi conjugation, which is very difficult to deal with. And the way we succeed is to go to this level instead of this one. And at this level, we might manage to deal with the computation. I don't know what I should say now. Maybe I will say what are the main steps. So the result, as I told you, is that locally these two objects are the same. So you will complain that I didn't explain how I cut it, but really it's the way we cut, we define this object. You have to see that it's cut into nice pieces. So how you prove the theorem? There is two steps. So first, you prove that this is an isomorphism modulo Pn when n is big enough. And that's here that I need the hypothesis, a place where I need the hypothesis that P is big enough. Okay, so you first prove that the two are isomorphic when you take this modulo a big power of n, and the second step is to show that the singularity of this object, are bound by the people which appear on the singularity of this object are bound. Okay, so if you have this result, you know that the singularity, the people of the singularity are not too big, and you know that for P for n big enough, you have this isomorphism. But if you have the two of that, you know that it's okay. So I think that it's better to stop here. Thank you very much.
Can you say a word? What was the connection between the mathematics stack and the
Okay, so the point is when you take a point of the emergent stack and you look at the versal ring at this point, this is a deformation ring I'm looking for. So it's as you mentioned, it's the version when I impose the Barsotti-Tate rate, and it's yes, yes, the part yes, it's really the local ring.
I mean, I know what is it dynamic,
but I think that you should work a little bit more in order to have a new proof of the Ariane Mezard conjecture. Yes, because now you have the ring, so you just have to compute. And as I told you, we have a very efficient way to compute that's an identity. We are not far. I think that this conjecture is true. For other type, right now I don't know.
So Xi is L1 G.
Yeah.
And so like for me, it looks like to look at sigma homogeneous classes, right? And then G and but only you are allowed to conjugate this as class G or L1 class G, depending on either the lower line or right?
Yeah.
So what the thing you prove is that, you say that it's much easier to prove the upper.
Yeah. Yes. I think that what I said is, in fact, the question by GL2 is very complicated. So I have no way to see what happens here.
Okay, well, I mean,
But the way that everything mixed here, no, everything mixed here, I have no idea. But
what are the geometric points of the portion? LG modulo the action of L plus 1 G by sigma conjugation. Or 5.
this one,
Like, yeah.
but okay. What it means? No, I don't understand the question.
Yeah, I don't know. I mean, like, when you allow to sigma conjugate by the whole LG, then comes like the PG, right?
Yeah.
But this is like much more complicated because you are only allowed to sigma conjugate by a small number. Like, can you describe the set of geometric points? Oh, set. Very, very complicated. Never wrote it. Because there was an article of Kiman version in class.
Yes, but I don't know what is this translation. But what I didn't tell you, which could be an answer to another question, but maybe it's related to your question. I told you I have we have some explicit formula, some naive equation. But in order to obtain the deformation ring, we have to take the phase saturation of this equation. And in fact, it's not very nice to take the phase saturation. We don't understand what happens when you take the phase saturation.
Sorry, so this all important, there are 4 separate.
No, this one after the phase saturation. But so I have equation before the phase saturation. I didn't say that because I have no style. But in fact, here at this level, I have a scheme and very explicit equation. But in order to obtain the deformation ring, I have to take the phase saturation. When I take the phase saturation, this big set of equation appear. But I have no control what I don't understand how the phase saturation works. So there is something still mysterious. And to pass from explicit equation at finite level, but maybe it's not related to your question. I tell you, if you ask a question, I give you an answer, but I like your question, I like my answer, so no, but I will look at the paper of Wim and tell you. So thank you.